Hi everybody, welcome to my 15th torsional bar video. In this video I'm going to be solving this situation you see here, and I'm going to be finding the minimum diameter of the shaft for spinning it at 3000 RPMs, delivering power of 160 kilowatts, and having the material having a max shear stress of 30 MPa. Okay, if you want to know something else about torsional bars, feel free to check out any of my torsional bar videos. So the first thing we want to do is just take a look at what variables we have, which ones we don't, and how we're going to solve for them. Alright, that's the case in these power sorts of situations. It's basically just manipulating variables and units until you get to the right answer. So the universal power equation is power is equal to omega times torque. Okay, that's the key equation we're going to use. And we know P, and it's spinning at a certain RPM, so we can convert that to omega, or radians per second. T, well, we don't know T, but we know that our shear stress max is that. So we need an equation relating our shear and our T. And that, of course, is this one, T R over J. Alright, and we know that radius, that's just diameter really, and J, that's pi by 2 radius, and you can convert the radius to diameter. So basically this is all we need. We can then plug this one into here and say power equals to omega T, well T is equal to tau J by R, tau J by R. Alright, we need diameter minimum, so let's just plug in, this in terms of the diameter. Actually, let's not. Let's keep everything in terms of radius. At the end, we'll just get an answer in radius, and we'll just times it by 2 to get diameter. Alright, so J in the diameter form is pi by 2, radius to the 4. So plug that into there, you get right, and then solving for radius, or just radius, solving for radius cubed, you get 2p pi omega t, and this of course would be the t max. Alright, over here too. Alright, now we can pretty well solve this, but we're left with this problem of omega here. Right, because omega needs to be measured in radians per second, and we're given it in RPMs. So let's say RPMs, that's, well, rounds per minute. We need to times this by a bunch of unit conversion factors to get to rads per second. So we're at minutes. Let's get that to seconds. Times by minute over second. There's 60 seconds in a minute. Got rounds per second. I want rounds. Rounds is just, going here, completing one full cycle. Well, there's 2 pi rads in that one round, or cycle, whatever you want to call it. Alright, so rounds per minute, that's usually n, times this factor here, 2 pi by 60 equals radians per second. Well, that was omega. So taking this, plugging that into here, and then straight away solving for R, we get 60p by pi squared n tau max. And this is a cubic root. Alright, so now it's just a matter of plugging in our values. R, well, we know that 2 times R is equal to D. So let's just solve this. D is equal to 2 times the cubic root of 60p. Well, it's 160 kilowatts. Kilo is times 10 to the 3. 160 times 10 to the 3. Again, putting everything in terms of its fundamental units, so we don't need to decipher what kilowatt per millimeter cubed is. You just put it in terms of meters, newtons, the fundamental units, so that when it comes out, you just get a nice answer in terms of meters. That's over pi squared rounds per minute, that's N, 3000 in our case, and the max shear stress, that's 30 MPa, again converting it to fundamental units. Omega is to the 6. It's a final expression. You can solve this. This of course would be our minimum diameter. Alright, if you would go any smaller than this, it would break. Turns out to be 0.044 meters, or you can say 4.4 centimeters, or why not 44 millimeters. Alright, and that's a pretty reasonable size. Alright, if you imagine 4 centimeters, that's not a whole lot. That's like your thumb, and maybe from, this funny little wrinkle out to here. So a diameter of about this much. Not a whole lot, but that makes sense. Only 3,000 RPMs. This answer totally is reasonable. Alright, so a quick recap. We realize we need to use the power equation, and we're given the shear stress. So we use this equation that we've seen before. We linked the two together. We expressed everything in terms of the variables we knew. And we realized that, hey, omega, it's not given to us in omega. We need to convert it to omega. So we did rounds per minute conversion, plugged it back in, rearranged. The whole time we're solving for R, we switched it to D, plugged in our numerical values, converting them to the fundamental units, and boom, got our final answers. Alright, hope this video helped you out somewhat. Any other torsional bar problem that I've seen is relatively straightforward. It's just a matter of juggling the units and juggling the symbols. Thank you, and I'll see you in the next video. I'm done torsional bars.